If I can't picture it, I can't understand it. अल्बर्ट आइंस्टाइन। वेलकम स्टूडेंट्स। न्यूटन्स लॉ में अभी तक हम स्टैटिक्स ऑफ पार्टिकल्स या ट्रांसलेशनल इक्विलिब्रियम की बात कर रहे हैं। इसकी जो मेन कंडीशन है, बॉडी पर लगने वाले सारे फोर्सेस का सम एक नल वेक्टर होता है। मतलब इन प्रॉब्लम को एनालाइज करने के लिए हमें बॉडी पर लगने वाले सारे फोर्सेस को ही एनालाइज करना होगा, इनमें एक्सेलरेशन नहीं होता। तो न्यूटन्स लॉ में एंट्री करने के लिए ट्रांसलेशनल इक्विलिब्रियम एक बहुत ही इजी वे है। यहाँ हम बॉडी का एबिलिटी बनाना अच्छे सीख लेते हैं। डिफरेंट काइंड के फोर्सेस को कब कहाँ कैसे लगेंगी, इनके बारे में हमें एक अच्छा आइडिया हो जाता है। इसके बाद अगर हम एक्सीलरेटेड मोशन की बात करेंगे तो वो समझना काफ़ी इजी होता है। जैसा लास्ट क्लास में डिस्कस किया था कि आज हम स्प्रिंग फोर्सेस के बारे में बात करेंगे। स्प्रिंग फोर्स क्या होती हैं उनको हमने लास्ट क्लास में स्टडी कर लिया था। आज उनको रिवाइज करते हुए उनके एप्लीकेशंस की बात करेंगे। स्प्रिंग फोर्स, हुक्स लॉ। रिलैक्स स्प्रिंग मतलब एक स्प्रिंग जिस पर कोई फोर्स नहीं है, वो अपनी नेचुरल लेंथ में है। इसी ऐसी स्प्रिंग को कई बार अनडिफॉर्म्ड स्प्रिंग भी बोलते हैं। अब अगर स्प्रिंग पर उसके लेंथ के अलोंग अगर बाहर की ओर फोर्स लगाया जाएगा तो स्प्रिंग की लेंथ बढ़ेगी। स्प्रिंग के अंदर की ओर फोर्स लगाया जाएगा तो उसकी स्प्रिंग लेंथ कम होगी। पहले हम एक एलोंगेटेड स्प्रिंग की बात करें। ये स्प्रिंग यहाँ से इस एंड से इसको पुल किया गया है और ये एंड वॉल पे अटैच्ड है। इफ यू सी द होल स्प्रिंग दैट इज इन इक्विलिब्रियम ट्रांसलेशनल, तो इस पर दोनों एंड से जो फोर्स लगे, एक हाथ ने फोर्स लगाया होगा तो इधर से वॉल ने भी उतना ही फोर्स लगाया होगा और ये दोनों इक्वल एंड अपोजिट फोर्सेस लगने चाहिए, तब जाके ये स्प्रिंग ये ट्रांसलेशनल इक्विलिब्रियम में होगी। अब हाथ ने स्प्रिंग की इस एंड पे फोर्स लगाया तो न्यूटन्स थर्ड लॉ से स्प्रिंग भी हाथ पर इस तरफ एक फोर्स लगाएगी और दैट वी कॉल स्प्रिंग फोर्स। ऐसी वॉल ने स्प्रिंग की इस एंड पर फोर्स लगाया तो स्प्रिंग वॉल पर इधर अपना फोर्स एक्सर्ट करेगी, दैट विल बी स्प्रिंग फोर्स। नाउ दिस force applied by wall and this spring force are action reaction pair, and this spring force and this applied force are action reaction pair, but this applied force by hand and this applied force by wall are in no way action reaction pairs, though they are equal and opposite. Now similarly अब spring पर एक compressive force लगाया उसकी लेंथ कम करने के लिए, so we call it compressed spring. अब देखिए इस हाथ से स्प्रिंग को पुश किया गया है तो एज इट इज फोर्सेस होंगे। पुश करने के लिए हाथ से स्प्रिंग पर फोर्स अंदर क्यों लगाया गया, तो अब ये वॉल को स्प्रिंग इधर पुश कर रही है तो वॉल इस पर इधर फोर्स लगा रही होगी दिस वे। अब देखिए ये दोनों ब्लू फोर्सेस स्प्रिंग पर एक्सटर्नल फोर्सेस हैं। स्प्रिंग इज इन इक्विलिब्रियम, तो ये दोनों फोर्सेस इक्वल इन मैग्नीट्यूड होनी चाहिए, अपोजिट डायरेक्शन तो है ही। अब ये हाथ पर स्प्रिंग भी एक फोर्स लगा रही होगी आउटसाइड और ये दोनों फोर्स न्यूटन थर्ड लॉ से इक्वल एंड अपोजिट होंगे। ऐसे ही वॉल पर स्प्रिंग फोर्स लगा रही होगी, ये स्प्रिंग फोर्स है, ये दोनों इक्वल एंड अपोजिट होंगे। नाउ अब स्प्रिंग का जो लेंथ में चेंज हुआ इसको हम बोलते हैं लॉन्गिट्यूडनल डिफॉर्मेशन। लॉन्गिट्यूडनल डिफॉर्मेशन, इट इज कॉल्ड आइदर एक्सटेंशन और कंप्रेशन। व्हाट इट इज, जस्ट सी इन द डायग्राम। ये इसकी रिलैक्स लेंथ या नेचुरल लेंथ से इधर कितनी लेंथ ज्यादा हो गई या इधर कितनी लेंथ कम हो गई, इसी एक्स को हम बोलेंगे लॉन्गिट्यूडनल डिफॉर्मेशन। हियर दिस एक्स इज एक्सटेंशन एंड देयर दिस एक्स इज कंप्रेशन। हाउ वी कैन डिफाइन इट? लॉन्गिट्यूडनल डिफॉर्मेशन एक्स इज द चेंज इन लेंथ फ्रॉम द रिलैक्स स्टेट। स्प्रिंग की रिलैक्स स्टेट से कितना लेंथ में चेंज हुआ, दैट इज कॉल्ड लॉन्गिट्यूडनल डिफॉर्मेशन। एंड व्हाट इज हुक्स लॉ? What Hooke's law states, the spring force is proportional to the longitudinal deformation in the spring. मतलब स्प्रिंग का स्प्रिंग फोर्स उसके लॉन्गिट्यूडनल डिफॉर्मेशन x के प्रोपोर्शनल होगा। ऐसी स्प्रिंग को हम लीनियर स्प्रिंग बोलते हैं। हो सकता है कुछ केसेस में स्प्रिंग फोर्स x के प्रोपोर्शनल न हो, दे आर स्पेशल पर्पस स्प्रिंग, बट जब हमें स्प्रिंग की बात होगी तो भले मेंशन किया हो ना किया हो, यू हैव टू अज्यूम लीनियर स्प्रिंग। Now just see, as Hooke's law says, spring force is proportional to kx, and here a minus sign. This minus sign denotes that spring force is opposite to x. So just see the red force is opposite to x. In again, this red force applied by spring is opposite to x. Now if you see the applied force, that will be equal to spring force, but it will be in the direction of x. So if you want to write applied force, F applied, it will be kx. Here k is known as spring constant or force constant or stiffness, and minus sign shows that spring force is opposite to the deformation. That is very simple idea regarding spring force. Now we will revise linearity property and result derived from it. Linearity in uniform spring. What does it mean by? Just consider a uniform spring in relaxed state, and for simplicity we considering only elongated state under spring. इसमें just we take two parts, say from here to here we take a length L01. It means of this part relaxed length is L1 naught, and for next part relaxed length will be L2 naught, and for the entire spring let us denote the relaxed length by L naught. So we are considering spring in two parts. First part relaxed length L1 naught, second part relaxed length L2 naught, and the whole spring relaxed length is L naught. And for first part stiffness or force constant is K1, for second part it is K2, and for the entire spring we assume the force constant to be K. Now this is what some terminologies we have defined for the spring and its two parts. Now let us see elongated spring. We have applied a force. Now the L1 naught will be extended and L2 naught will also be extended and L naught will also be extended. Means entire spring will be extended. Now for uniform spring, what does it mean by uniform? So extension will also have uniformity. Or you can say this diagram is a isotropic, this longitudinally isotropic extension. मतलब हमने ये डायग्राम पूरा ऐसे लेंथ वाइज एक्सपेंड कर दिया, तो हर लीनियर डायमेंशन अपनी ओरिजिनल डायमेंशन के प्रोपोर्शनल चेंज हुई होगी. नाउ लेट अस सी व्हाट से दिस L1 not become L1 and L2 not will become, say, from here to here L2, this one, and say this entire length L naught becomes L, and let us denote change in L first part length, this x1, and entire spring x, say this is x1, and what is the length of change in this part? It will be x minus x1. Please note, if you denote it x2, x2 will be what? X minus x2, because this point shift x1 and this point shift x. So what is net difference change? X minus x1. Now as we define linearity or uniformity, means every part changes its length proportional to its initial length. So what we can say, L1 by L1 naught must be equal to L2 by L2 naught must be equal to L by L naught. So that is linearity. Here forces we can show. This applied force and red is the spring force. Again this is force applied by wall. These two forces, blue forces, keep the entire spring in equilibrium. Now on the wall spring also apply this force. Now just see, if you are considering these two parts as a separate, so this part will apply force on this part and this part will apply force on this part. Let us see how the forces are. Say this part, and this force is the force applied by this one part by on two, means by the left part on the right part. Similarly, this is the force. This is the force applied by this second part on the first part or by the right part on the left part. Now these two forces we have seen, they are equal. Every portion will get extended in the same ratio. That is what we mean by linearity and uniformity. Every portion will get extended in the same ratio. So what we can say, the L1 by L1 naught will be equal to L2 by L2 naught and it will be equal to L by L naught. L1 by L1 naught is equal to L2 by L2 naught and so on is equal to L by L naught. Why we have seen so on? Here we have assumed, for example, two parts. We can assume three parts. We can assume n parts of a spring. So for every part, the final length upon initial length of that part, this ratio will be a constant, and that will be the same as for the entire spring. And this is what called linearity in uniformity. Now from each part, we can subtract minus 1, minus 1, minus 1. Suppose we'll take minus 1, take LCM L1 naught. So what you get here? L1 minus L1 naught. So L1 minus L1 naught is what? Change in length of the first spring, it will be x1. As see L2 minus L2 naught will be what? Change in length of the second part, we can say it x2. As see L minus L1 naught upon L naught. So L minus L1 naught is the change in the entire spring, that is x. So what we can write here? By the same property we can write equal fractional change in every portion. So L1 minus L1 naught upon L1 naught is fractional change in the first part. L2 minus L2 naught change in second part upon initial length L2 naught is fractional change in the second part. So L1 minus L1 naught upon L1 naught, that is a fractional change in the first part. Similarly, L2 minus L2 naught upon L2 naught is a fractional change in the second part. And similarly, L minus L naught upon L naught is a fractional change in the entire spring. And why we kept here dot dot dot? It means if we had considered more than two parts, suppose there were L3. So what we written here? L3 minus L3 naught upon L3 naught. And for another part, Ln minus Ln naught upon Ln naught. So for every part, fractional change in length will be same, and this property is derived from the first equation. What? Every part will change its length in the same ratio. Means final length of a part upon its initial length, this ratio will be constant for the entire spring. For parts of a spring, last class we have concluded that, see here, K1 L1 naught is equal to K2 L2 naught and so on is equal to KL naught. What does it mean? That in relaxed state, if we consider different parts of a spring, then product of force constant of that part and relaxed length of that part is same for every part. That is K1 L1 naught is equal to K2 L2 naught. Here it should be K2, this typing mistake, and that will be equal to KL naught. Similarly, we can write in elongated state also. So what? K1 L1 is equal to K2 L2 is equal to KL. K1 L1 is equal to K2 L2 is equal to KL. So please keep in mind here it should be K2, this typing mistake. Now that we have very important relation for the spring, now we are coming on a uniform elastic cord. So what is difference between spring and elastic cord? Both can be extended. But if you try to compress a spring, you can compress it because the spring will apply reverse force. But if you try to compress a elastic cord, it will bend because of its flexibility. So that is a very striking difference. All the above ideas will hold true for a uniform elastic cord for extension in length. Just keep for extension in length, because an elastic cord can only be extended. It cannot be compressed because of its flexibility. Keep in mind that a cord cannot be compressed in length as it is extremely flexible. So when you are dealing with cord, keep in mind that it cannot be compressed. It can only be extended. Now we are coming after revision of all these things. Let us try to apply these ideas in practical situations, and that we'll discuss with some examples. Example 1. A block of mass m placed on a frictionless horizontal floor is connected to a fixed support with the help of a spring of a force constant K. The block is pulled by a rope as shown in the figure. The pulling force is increased gradually without changing its direction until the block loses contact with the floor. And that is the idea. You can see the diagram. Here the block is connected with the wall with a spring. Here it is connected, here it is connected. Now this block is being pulled with the help of this thread. and this pulling force is increased gradually, very gradually, keeping this angle fixed because we have to keep the direction of force constant. We are not changing theta, only we are increasing the force pull. What it finds? Well before the block loses contact from the floor, draw free body diagram of the block. B part. What is the necessary tension in the rope so that the block loses contact from the floor? And C part. What is the extension in the spring when the block loses contact with the floor? Now we have to analyze these three parts, and you can see we have to consider spring force also, because as the force is increased, this block will shift here and the spring will extend, and till a moment this block will start rising. Initially the block will not start rising because there is weight. So it is obvious that this force tension, its vertical component will try to lift the block. So, and this spring force is horizontal. So this spring force is nothing to do with the lifting of the block. So the moment when the vertical component of spring tension, that is string tension, will become equal to weight, after that the block will start rising. So that is the idea behind it, and let us try to understand how we'll use it. As the pulling force is increased gradually, the block shifts towards the right so slowly that its acceleration can be neglected at every instant of time and be assumed in equilibrium at every instant of time. It means, just see this word increase gradually, moving gradually. This word you will find later on so many times. So what does it mean by gradually? In gradual movement, the movement is so gradual that every instant of time you can ignore its acceleration. So if acceleration of a body is ignored, it is negligible, then it can be treated in equilibrium. So whenever there is gradual movement, always treat the body in equilibrium at every instant of time. Now that is a key idea behind gradual increase or gradual movement. So please keep in mind this gradual movement you have to encounter several times in further problems. So here we again redraw the diagram here. So that is the diagram initial state. At present there is no force by the hand, only just this hand is used to keep the thread straight. Now just force is applied, so this block will shift, and it will shift by an amount x. So that is what we are not considering that it is going to lift here, just it is something x. So what are the forces acting on it? You can see force applied by hand, F, and the same force string will apply on the hand. So spring tension T will be equal to F. This. So later we cannot, we should denote by F here. We can see T or F also. So we draw it F. F means spring tension here. This F, that is the spring force. Next force is spring force. Here it is extended, so spring force be opposite to x. The spring will pull the block towards the left. Now normal action from the ground, and last one, the weight of the block. It means true weight, the gravitational pull from the earth. Now these are the four forces acting the block: the string force, tension F, normal action from the ground, this spring force, and weight. Now how these forces will change when we further pull the block? As we further pull the block, this F will increase, Kx will increase, and as F will increase, you can see its vertical component will increase, and this vertical component will try to neutralize mg. So we have discussed earlier that the moment vertical component of this force F will become equal to mg, the block will start rising, or it will leave the contact with the floor. See here, this F cos theta is the horizontal component of this force F, F sin theta, vertical component of the force F. Now, translation equilibrium of the block A, for what we can write, summation Fx equal to 0. What is denote? That is this F cos theta. In x direction, there is this force F cos theta and Kx. So they must balance each other. So f cos theta must be equal to kx. F cos theta equal to kx. That is equation 1. Now what we can write for summation Fy equal to 0. In y direction there is this force and this force and this force. Just see this n and f sine theta in upward direction and mg is downward direction. So sum of these two upward forces will be equal to mg. So what we can write here? N plus f sine theta is equal to mg, equation number 2. Now what these equations suggest? See, as f increases without change in angle theta, equation 1 reveals that extension x and hence the spring force must increase. जैसे आप f को इंक्रीज करेंगे, थीटा चेंज नहीं हो रहा, कांस्टेंट है, तो f इंक्रीज होगा तो x इंक्रीज होगा, because here k is also constant. And what equation 2 reveals? Equation 2 reveals that the force of normal reaction n must decrease. Why it must decrease? Because n plus f sine theta sum is a constant, because mg is a constant. So if you increase f, theta is same, so this term is increasing, so this term will decrease. And as we said earlier, we keep on increasing f, a time will reach when f sine theta will be equal to mg. At that time n will be 0. So that is the required condition of losing contact. When a body is losing contact with some other body, at that time normal reaction is 0. Just see one thing, being normal reaction is 0 does not mean that it will lose contact. It means there is no pressing force between them. But if it is about to leave contact, at that time normal contact force between the bodies must be 0. So here the two bodies which are losing contact are the floor and the block. So when the block is about to leave the contact from the floor, at that moment, immediately before that moment, normal reaction from the floor must vanish. It must become a null vector, or it must become 0. Therefore, when the block is about to leave the contact with the floor, the force of normal reaction must vanish, that is, become 0. That is very clear-cut idea. And please keep in mind, this idea you have to again use at so many times in further problems. Now we can draw the free body diagram, FBD when the block is about to leave the contact. So in this condition, n will be 0. And f has become so large that f sine theta is equal to mg. So how can we draw the FBD? So here the block, mg, say these two lines. Now from here to here there will be f at the same angle theta. So we can show the f, this. Now we can show both the components of f. This length will denote the f sine theta vertical component of f, and you can see from here it is equal to mg. F sine theta. So here f cos theta, and this f cos theta will be balanced by the spring force, because in this direction there is no other force. So that is the free body diagram of the block when it is about to leave the contact. So at that time you can see n is 0. We expand why n is 0. Now we can come on the B and C part. For that this FBD will be required, so we will reproduce it. B, what is the necessary tension in the rope so that the block loses contact from the floor? C, what is the extension in the spring when the block loses contact with the floor? These two parts we have rewritten. So what is the block remains in translational equilibrium immediately before it loses contact, or it leaves the contact with the floor, because we have seen earlier the shifting of the block is very gradual. Gradual means it is infinitely slow. So at every instant of time its acceleration can be neglected, and if acceleration can be neglected, it can be treated almost in equilibrium, not perfectly equilibrium, almost. But almost means sum of all the force will be 0. So equation will be as it is if it were in perfectly equilibrium. Please keep in mind, it is not in perfectly equilibrium. Translational equilibrium of the block at the moment it is about to leave the contact. We have reproduced the free body diagram. You can see again mg, we have drawn these two horizontal lines. Now f start from here to here. What it shows that the vertical component of f sine theta is equal to mg. So there is no n. And here f cos theta is equal to kx. Summation fx is equal to 0. What does it mean? F cos theta is equal to kx, equation 1. Summation fy equal to 0. What does it mean? F sine theta is equal to mg. Because here is no n. Now from these two equations we can write required answer from of B and C part. From equation 2, what we get? Necessary force, that is tension in the string. What is R in B? What is necessary tension in the rope so that block loses contact? So here F is equal to mg upon sine theta. Very easy. Now we are coming on the C part. What is extension in the spring? So we'll use equation 1 and substitute this value of F. Using the above result in equation 1, we get the necessary extension in the spring. What? X is equal to F cos theta by X. F is equal to mg by sin theta. So sine theta and cos theta. Cos theta upon sine theta will become cot theta. So it will be X is equal to F cos theta by K, because here F cos theta by Kf, and now is substitute value of F, mg upon sine theta. So mg by K and cos theta upon sine theta will become cot theta. So mg cot theta upon K. So that is result of C part. Now you can see how simplicity with we have solved this problem. And here, other than using these usual equations what we are writing for equilibrium, we have learned two very important terms: gradual movement. So whenever something is moving gradually, we have to ignore its acceleration at every instant time, and we have to treat the body in equilibrium at every instant of time. That is what does it mean by gradual motion. And second, what we have learned, when something is about to leave contact with some other body, the contact force between them must be 0. If there is no friction, so the contact force is the only normal action. So at that time, normal action will be 0. If there is friction, so at that time, normal action as well as friction, both will be 0. Now we're coming on the next part, next question. Example 2. A block of mass m is held between two springs of force constants K1 and K2. As shown in the second figure, the block is allowed to shift downwards gradually till it stays in equilibrium due to the spring forces. Calculate the downward shift x of the block. It means diagram is given here. There are two figures. Here you can see this spring is suspended from the ceiling, and here this spring is attached from the floor. It is that. Now just see, there are no other forces on the spring, so both the springs are in relaxed state. One thing is, we have treated the spring to be massless. So till or until it is not specified that a spring has mass, treat it massless. So this spring is massless, so there is no force, so it will be in relaxed state, and this spring also be in relaxed state. Now we take a block of the size exactly the gap between the spring. So inserting this block and attaching this will not create any exchange in these two springs. Now this block is held here in equilibrium and then allowed to shift downward. Allowed to shift means, now to hold this block, this man has to apply some upward force that is equal to weight. Now if the man start decreasing his upward force gradually, the block will shift very gradually, with infinitely slow speed. The block will slow down, and as the block shifts down, this spring will get extended. So this spring will start pulling the block upward, and this spring will get compressed. So this spring will start pushing the block upward. So both these forces are in same direction, so they will add up. The moment when sum of these two forces will become equal to weight of the block, at that time there is no need to apply a force by this man. So he will remove his hand, and at that time, at that position, the block will stay in equilibrium as shown. We'll see later on the same diagram and just see what we have thought here. This thought is necessary to proceed with the solution. Now, before we proceed with the solution of any problem, try to analyze the entire problem process. What is happening? What is the process in the problem? The same kind of thinking, process thinking we have executed in the first example. Now just see what the process is to be going on in a problem. If you are able to decode the process exactly, certainly you will solve the problem. Now I am suggesting you, in any problem where you stuck up, whether there will be some calculation mistake or you will analyze the process incorrectly. So please be very careful before start proceeding on solution. Try to analyze the entire process very critically. So here what we have done, thought we can represent here in diagram. Just see here. Suppose by shifting an amount x, the block stay in equilibrium. So this spring you can see is compressed and this spring is elongated. So if this spring is elongated, it means it will pull the block upward. And this spring will push the block upward. What is force by this spring? K1 into x upward. And by the force, what is the force by this lower spring? K2 into x upward. Because for both, its extension x is equal to its compression. And here is the weight mg. So we can draw the free body diagram. Now mentally we have drawn the free body diagram. Now why I am suggesting to think the process. Actually, in thinking process, you will think the free body diagram also in gradually by attempting so many problems and by ample amount of practice. In so many situations, you will be able to conceive the ability in your mind and you will be able to write the necessary equation without drawing ABD, and it will be great saving in time. So here, translational equilibrium of the block. The block we are redrawing here. This spring force by upper spring K1x upward. Now from downward K2x, the lower spring is pushing it upward. And the third force is weight mg. There are only three forces. And we can write summation Fy equal to 0. So what the equation will be? This force upward, this force upward. So their sum will be equal to this downward force mg. So equation will be K1x plus K2x is equal to mg. And let us see. Summation Fy equal to 0. What it will be? K1x plus K2x is equal to mg. Now, what is required? By just analyzing problem, will become so habitual in qualitative thinking that without drawing this ABD, you will be able to write this equation. And here is the same time setting. Now from here we can write what is x, mg upon K1 plus K2. The problem was quite simple. Now we will take slight modification in this problem. Example 3. What modification is? Ends of a uniform light spring of relaxed length h and stiffness k are affixed between two fixed supports. A washer of mass m that can slide on the spring is lying at the lower support. The washer is raised to the mid height between the supports, glued with the spring, and then allowed to shift downwards gradually. After shifting a depth x, it stays in equilibrium. Find x. Now in the what is modification? In previous problem there were two springs, upper spring force constant K1 and lower spring force constant K2. Here there is one spring. How it is, you can see. Here this spring is vertically fixed between ceiling and the floor, and here is a washer, and washer means there is a hole in between here, and this washer can be moved up and down without touching the spring. So someone lift the washer to mid height, say h by 2, and if you release the water, it will fall down because it can slide on the spring. But what he does, he glues the washer here with the spring. Glues means you can put some Fevikwik, the washer will be glued here. Now if you leave the washer will come down and it will extend the upper part and compress the lower part. So you can see the change, modification. In the previous part, there is one spring here, one spring here, and there its force constant was K1, its force constant was K2, but now this washer is glued. So on the washer, the upper part applies separate force and lower part will apply separate force. So we have to find force constant of the upper part as well as force constant of the lower part, and these force constant are not given. The force constant of the entire spring is given. Here is the idea you have to use. What? K1 L1 naught is equal to K2 L2 naught is equal to KL naught. Means product of force constant and length of a part is the same for every part in a spring. Now let us see how we'll solve it. So if you leave the washer, shift down gradually, so it will stay at some depth h in equilibrium under the upward push of the lower part of the spring and upward pull of the upper part of the spring. See, this way. If you leave it, see here. So this part has been compressed and this part has been extended. Force constant K dash of both the parts. Why I am saying both the parts? Because both the parts are equal in length initially. So you can say their force constant must be equal. One thing you have to keep in mind, because we have written two equations there, one involving the K and initial relaxed lengths of the parts and other K into final lengths. You may have a doubt that why can we write K of this part into this length is equal to K of this part in this length. Actually here we cannot do. Why? Just see the derivation. In every part, spring force was same when we derived that result. But here, in this part, we cannot say spring force will be same as of this part. So if the spring force are not same, so we cannot use that relation. So please keep in mind. So when you write KL product is equal to same for entire spring, it is safe to take the initial lengths, relaxed length part. Now what we have? K1 L1 naught is equal to K2 L2 naught is equal to KL naught. So here you can see it is K dash, it is also K dash, and part L1 naught is what? H by 2. L2 naught was H by 2, so write only one term. K dash into H by 2 is equal to K into H. And from here K dash is 2K. It means shorter is the part of the spring, more is the force constant. And longer is the part, smaller is the force constant. Now we can analyze the translational equilibrium of washer. How we can analyze? Upper part is pulling it upward. So what is K dash X? And lower part is of a spring is pushing it upward. What is force? K dash X and mg. So these two upward forces will balance mg. So we write equation summation Fy equal to 0. So K dash X plus K dash X means 2 K dash X is equal to mg. Now let's substitute value of K dash, what? 2K. So 4kx is equal to mg. So what is x? Mg by 4. Substituting K dash from equation 1, we get x equal to mg by 4k. Just see a slight modification. And now let us come somewhat more modification in the same problem. And with that modification, we take in the next part. Example 4. Ends of a uniform light elastic cord of relaxed length h and stiffness k are affixed between two fixed supports. A small bead of mass m that can slide on the cord is lying at the lower support. The bead is raised to mid-height between the supports, glued with the cord, and then allowed to shift downwards gradually. After shifting at depth x, it stays in equilibrium. Find x. Now modification is what? Here we replace the spring by a cord elastic, and that is situation given. This bead can slide on the wire without friction. So here is the bead initially. Now someone lift the bead to the mid height, h by 2 you can see, and there he glued the bead here. So bead will be glued. Now if you release the bead, what will happen? The bead will pull the upper part, extend its length, but it cannot compress the lower part. Here is the change. The lower part will simply bend by flexibility, so it will not apply any force. So bead will stay in equilibrium only because of upward pull of the upper part. And we'll just see. Again, this is the qualitative understanding of the process. And this qualitative understanding is necessary to proceed with the solution. More comfortable you will be in such kind of qualitative understanding of the process, more comfortably you will be able to solve a problem. Now let's see what we'll do. Say this way. This bead has pulled the upper part, but the lower part has been slackened or bent. So bending a rope or bending a cord, it becomes slackened. Slackened means it is bent and it is not able to apply any force. Now we can see here force constant K dash of both the parts. Actually, force constant of both the parts will be same, but lower part will not apply force. So these two parts are identical. So again we have what? K1 L1 naught is equal to K2 L2 naught is equal to KL. So K1 K2 are same, say K dash, and L1 naught and L2 naught are same as H by 2. So what we have? K dash H by 2 is equal to KH. So what is K dash 2K? Equation 1. Now we'll analyze translational equilibrium of the bead, T of the washer. So here it should be bead. So that is what typing mistake from the previous part. So bead, here only the upward pull from the upper part of the cord, and there is no force from the lower part, and here is the mg. Now very simple solution. Summation Fy equal to 0. So K dash x is equal to mg. And substituting value of K dash from the equation 1, will find x. What? X is equal to mg by 2k. Now these three parts, or this problem with these three modifications is necessary to do. So what we learn? Use of the formula KL product is the same for every part of the spring, this one, and an elastic cord cannot be compressed. These two learning from these parts. And from previous part, when something is about to leave contact with the floor, at that moment normal action will be 0. And again, in all these problems, 4 problems, there is gradual movement. Gradual movement means the body is moving so gradually, so slowly, that every instant time its acceleration can be neglected and it can be treated in an equilibrium. Now with this amount of understanding, let us proceed on the next question, example 5. What is that? One end of a light spring of natural length 3r by 4 is attached to the lowest point O of a frictionless semicircular wire track of radius r fixed in a vertical plane. A small bead of mass m, which can slide on the track, is attached to the other end of the spring. The bead is held stationary at a point P such that the spring makes an angle 60 degrees with the vertical. The spring constant K is equal to mg by r. Find the additional force needed along the spring to hold the bead in equilibrium. Now, here diagram is given in the problem. So here, this is a wire track. On this wire track, this bead can slide. Now there is spring. Lower end of the spring is attached here at the lowest point of the track. O is given here, and the upper end is attached with the bead. And relaxed length of this spring was what? 3r by 4. Now the moment when it makes angle 60 degree, the bead is held in equilibrium. Means someone is holding means it is holding as well as applying force, and the force is applied, this you can see here, along the spring. So the necessary force to hold this bead in equilibrium is applied in this way. Actually, this force can be applied in any way, but here a specific condition is given. Now, how we analyze here? For analyze, we had to see all the forces on the beat. Now let us come on the again qualitative understanding of the process. Now on beat, how many forces might be acting? One is a normal reaction from the track, and this normal reaction will always act toward the center of the track. Other one is the spring force. Next one is the weight of the beat, and last force is what? The applied force F along the spring force. So we have to consider all these four forces, and let us see which force will have what amount. But before, we have to find spring force, and for a spring force we have to find extension. So we have to find length of the spring in this condition, and this is only geometrical consideration. So till so far what we have thought is the qualitative understanding of the process involved in this problem. If till that moment what we have discussed you are comfortable to think, then you can proceed with the solution. Now again let us repeat, summarize the thing. Here the spring, so spring must be extended or compressed. So if it is extended, it will pull downward. If it is compressed, it will push here. So that is what spring force. And there may be some normal reaction, maybe. And if there is normal reaction, it will act certainly toward the center. And mg, and the necessary force additional is here in this direction, either in this direction or that direction. Now, for all, first we have to find a spring force, and for that we have to find extension. That is, we have to find present length of the spring, and by difference of this present length we will find extension or compression. So only geometrical consideration. We have redrawn the diagram again here. Now geometrical consideration. What are? Let us locate the center C of the track. Say here center C. If we join C and P, that is water radius, and the normal reaction will be in this line. Let us join C and P. If we join C and P, what we can say? This is R, this is R. So this angle 60, this angle will also 60, this angle will also 60. So it is an equal triangle. Let us again think. CO is R and CP is R. So this angle and this angle not shown for clarity here, it will be 60. So third angle will also be 60. So angle triangle COP or OCP is an equal triangle. So all sides will be equal to R. So present length of the spring will be equal to R, and relaxed length was 3r/4. So spring is certainly elongated, and spring is elongated means it is pulling it this way. That idea is clear. So let us coming on calculation part. Triangle OCP is an equilateral triangle. What it shows that the elongated length of the spring is OP is equal to R. Why we got elongated before finding R? Because we are saying it is R and relaxed length is less than R, 3r/4. Now we can find extension. So extension X in the spring, what? X is equal to OP minus 3r/4. OP means extended length minus relaxed length. So R minus 3r/4, it will be R/4. So it is extension. It means the spring must be pulling the bead in this direction. Now we can analyze the translational equilibrium of the bead. So let us draw its free body diagram. Translational equilibrium of the bead. Say here we have drawn the required geometry O and C only because to show the normal direction towards C and spring force towards O. So these two directions we have drawn by dashed lines. So that is normal reaction. By the track, spring force mg/4, mg, and we can see certainly the resultant all of these forces must be somewhere here in this direction. So pulling force is here. Now it is given condition the pulling force has to be applied along the spring. So opposite to mg/4. Now let us see that force F. Here you can see xy component. Analytical method you can do. Assume here x, it is y, summation fx equal to 0, summation fy equal to 0, make equation and try to solve the answer. But here we can see some very simple thing. What? If you see the what is angle between N and mg, this is 60, this 60, this is also 60. So this angle is what? 120. And similarly, this angle will be 120 and this angle will be 120. And now we can use that idea. If three vectors, their sum is 0, and angle between any two adjacent vector is 120, then all the three vectors must be equal in magnitude. Let us see how we can incorporate that idea here. mg by 4, 60 degree, 60 degree, and n, 60, 60, and this is f. Now just see here. Here the net force is what? F minus mg by 4. So what are the three vectors? mg, n, and f minus mg by 4. All these three forces are acting simultaneously on the bead and maintaining the bead in equilibrium. So their sum is 0, and angle between any two adjacent, you can see 120. So they must be equal in magnitude. So if sum of three vectors is a null vector and angle between any two adjacent vector is 120 degree, the three vectors must be equal in magnitude. So what we can write? mg is equal to n is equal to f minus mg by 4. So this force and net this, what? F minus mg by 4, they must be equal in magnitude. So by the first and the last term you can find f. F is what? mg plus mg by 4. So f is 5 mg by 4. So just see again here, by using geometrical considerations, sometimes it will be necessary and sometimes it will be a luxury. Why I am calling it luxury? Because if you have written summation fx equal to 0, summation fy equal to 0, even though you can find the answer, but it will require a little bit amount of time. But here you can do it orally. And the same thing we have seen earlier, because what? If there is story of three vectors, then it is better to use geometry. In equilibrium, if sum of three forces is a null vector, so these three forces will constitute a triangle. So at that time you can use a triangle law, or in some other way, in this way also. So in solving equilibrium, dealing the three forces and they are using geometry, I am saying it's a luxury. You can save great amount of time. Now we are coming on the next part, next question. Example 6. Three springs of force constants K1, K2 and K3 are connected one after another as shown. The free end of the first spring is attached to a fixed support and the free end of the third spring is pulled to produce a total extension X in all the springs. Total extension X means sum of extensions of all the springs is X. Now this situation is given. So this is K1 first spring, K2 second spring, K3 third spring. One end of the, that is what, free end of the first spring, this is fixed support. Now it is not free. And free end, now this end is free. It is held and pulled to create an extension. What you have to calculate here? A, find extensions in each spring. So X is total extension. So what, how this X will be divided among this spring, that you have to calculate. Solution. Let us consider the diagram as it is, and now we have consider the diagram just in parallel to it in elongated state, so we can compare the extension. So here we have pulled. So what is total extension? Here is x1. So this is what, this point we have assumed shifted x1. Now we assume this point has been shifted here by an amount x2, and this point is shifted here by an amount x. Now you see, x is what? Does it extension spring 3 or total extension? Actually, suppose we start thinking from the first spring, this end is fixed. So how much this end will shift is the extension in spring 1. So x1 is the extension in spring 1. To find extension, if one end is fixed other end is moving, so shift of that moving end will give you directly the deformation. But if one end is not fixed, then vectors difference of the shift of the two ends will give you the deformation. I'm saying vector difference. If the shift in two ends is opposite, add them. If the shift in two ends are in the same direction, subtract them, and in that way you'll find extension. And suppose this end of this spring has shifted x2. So by this logic, you can see what is extension in the second spring. It is x2 minus x1, because this end shifted here and this end shifted here, so extension is x2 minus x1. Similarly, you can write extension in the third spring, that is x minus x2. So we have thought about extension. Let us come think about the forces. Say, let us write first extension. Extension in this first spring is x1. Extension in the second spring, spring 2, is x2 minus x1. And extension in the third spring, spring 3, is x minus x2. Please keep in mind. Now let us show the forces. Suppose by hand a force F is applied, so spring will apply the same force F here. F. Now this blue force is applied by the third spring. So this third spring will pull the second spring by the same force F. This. And the second spring apply a reaction force F here. I'm showing rate. Just blue by for third spring, rate for second. But all these F are equal. Now this second spring will pull the first spring here with the same force F. And the third spring will apply a reaction here F. Now no need to show the forces here. So these are the forces developed. So in all the spring, forces are same. Tensile forces are equal in all the springs. Since all spring forces are equal, we can write here by saying equal means equal in magnitude. Of course, they are not equal in direction. F is equal to K1 x1, because K1 and extension in spring 1 is x1. What is force for second spring? K2 and extension in second spring, K2 x2 minus x1. It's equal to K2 x2 minus x1. And what is spring force in third spring? K3 into extension in third spring, K3 into x minus x2. K3 into x minus x2. Now we have, actually we have how many unknowns? X1, x2 are unknown. And by making suitable equation, you can solve. By making these suitable pairs from here, you can solve for x1, x2, x3. Now I'm writing the answer here, and solution of these equation is merely algebra. I'm leaving it for you. By solving the above, we get extension in spring 1 is equal to K2 K3 x upon K1 K2 plus K2 K3 plus K3 K1. And similarly, extension is spring 2. Now this result is having great deal of symmetry. Denominator term you can see. Numerator, there is product term, but there is no K1. So by this symmetry, you can write for a spring extension 2, that is K1 K3 upon the same denominator, and that is same K1 K3 into x upon K1 K2 plus K2 K3 plus K3 K1. And similarly, we can write extension in spring 3, that is K1 K2 into x upon K1 K2 plus K2 K3 plus K3 K1. Now these are the spring extensions. And what is a striking feature here? This one. Please pay attention here. Now we are going to solve B part. What is B part? If it is desired to replace the combination with another single spring, what should be the force constant of the new spring? If you want to replace the combination by a single spring, what does it mean? In that single spring, there should be the same force for the same x. So we can call it equivalent spring. What we do here, again we take the previous things what we done, initial state, elongated state, and x1 shift in the free end of the first spring, shift in here x2 and shift in here x3. Now we can show forces as we have done earlier, this and this. No need to explain again. Results obtained in the previous part. What extensions in the spring? Extension in this first spring was, remember, there was the denominator was same, product of two springs constants, and the numerator K1 is not present in the extension of spring 1. So it is what? K2 K3 x1 is equal to K2 K3 into x upon K1 K2 plus K2 K3 plus K3 K1. Similarly, extension in the spring 2, again I am drawing here, it is x2 minus x1 is equal to K1 K3 into x upon K1 K2 plus K2 K3 plus K3 K1. Similarly, extension in the spring 3, x minus x2, so it should be x, it is x not x3, x minus x2 is equal to K1 K2 x upon K1 K2 plus K2 K3 plus K3 K1. Now let us come on one interesting discussion. Say read it x. X is what? Total extension in all the springs. So if you add all these extensions, you get x. This will cancel here, only this will remaining. If you add, this is x. Now we want to replace this combination by a equivalent spring. So what is that? That spring must create the same spring force with the same extension x. So spring force in every part is same. So most simple way to write spring force is what? With that. So what is K1 into x1? So K1 into x1 is what? K1 K2 K3 upon this. So we write here K1 into K2 K3 into x upon K1 K2 plus K2 K3 plus K3 K1. So it was K1 into x1 is equal to K equivalent to x, and you will cancel x or x. So what you will find? K equivalent K1 K2 K3 upon K1 K2 plus K2 K3 plus K3 K4. Now in that way, writing expression for the equivalent spring constant for 3 springs, you can this way. If there were 2 springs, what you written? You may think K1 K2 upon what? You will make K3 0, so it will be 0. So it is better to generalize this relation. Let us take reciprocal on both the sides. So if you take reciprocal on both sides, you will find very simple relation. 1 upon K equivalent is equal to 1 upon K1 plus 1 upon K2 plus 1 upon K3. And if there were 4th spring, 1 upon K4. If there were 5th spring, 1 upon K5 and so on. So if there were only 2 spring, what it were? 1 upon K1 plus 1 upon K2. You can see this relation is similar to parallel combination of resistances. You might have studied in 10th class, current electricity. Though it is series-like connection, but the result is something parallel resistance connection. So when springs are connected like that, one after other, we can replace the combination by a single spring of force constant given by this. So this result we can use in several problems, and we call this kind of combination a series combination of spring. So let us summarize what we have learned in this problem. Series combination of springs. What is that? The spring is connected like that here, and if you extend, forces will be developed in the spring, and every spring force will be same. And the same thing you can think if you have compressed it. Again, the forces must be in opposite direction, but again the forces will be same in every spring. So what we can conclude? Springs are said to be connected in series if they are connected one after other in such a way that total extension of the combination is the sum of extensions of each spring. That is very important thing. What should be the total extension? It should be equal to sum of extensions of each spring. And what is the second point? Force of each spring must be equal. Spring forces developed in each spring are equal in magnitude. And what is third? The combination is replaced by an equivalent spring. The force constant of the equivalent spring is, and we have derived the relation 1 upon K equivalent is equal to 1 upon K1 plus 1 upon K2 plus 1 upon K3 and so on. So in this way you can simplify, and this, please remember, this is called series combination of spring. And how you remember formula? This formula is analogous to parallel combination of resistances. So if resistance were connected in parallel, what is equal resistance? 1 upon R equivalent is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. The only difference is what? Parallel combination of resistances formula is equivalent to series connection of springs. So that is very important idea, and so many times it will be very helpful to use. Now we can think if there is a series connection, so there may be parallel connections. Let us see what will be in parallel connection. So without mentioning parallel connection, let us try to take an example, because what I have done here, without mentioning series combination and making you to learn and using it, we have taken a problem, we have reduced the all results, and now these things become obvious to us. So same strategy will take what? To analyze parallel combination. We take an example, and please forget that we are going to discuss parallel combination. We are taking, say, independent problem. Example 7. The block shown in the figure is in the state of rest and all the springs are relaxed. The block is displaced by a small amount x towards the right. Say this is the block. This spring is K1, this is K2, this is K3. Certainly you can say they may be in parallel, but what about this? You can see geometrically they are parallel, but what about this? These are in series, these are in series. Let us see, analyze it, because parallel combination is very interesting. Find the net force F applied by all the springs on the block. Say again we have reproduced the same diagram here, and now parallel to it we will draw diagram in which we assume the block to be shifted by an amount x here towards the right. See this way. Now this end will shift here by x. Similarly, this end will shift here by x. So what it shows? Extension in these two springs is same x, and that is equal to compression in these two springs. Now we can show the forces. So this spring will extend it, so it will pull the block here towards left by K1x. This will pull by K2x. This will push by K3x. K1x pull, K2x pull, and K3x push, because this spring is compressed. What we can see here, extension in all the springs are same, and forces of all the springs are in same directions, though forces may or may not be equal. Here, if all the force constant were equal, the forces were equal. But here force constant are different, so forces are different. But what is the striking thing to note? That all the forces are in same direction. And another thing is what? Deformation in all the springs are of same amount, though few springs are elongated and few springs are compressed. So what we can write about net force? All the spring forces are acting on the block in the same direction. So the net force on the block is F net is K1x plus K2x plus K3x. Now we can take x common. So what will F net? K1 plus K2 plus K3 into x. So what we have observed here, deformation in all the springs has the same magnitude. I'm not saying same deformation, because same deformation means it may be understood that all are extended or all are compressed, but some may be deformed, some may be elongated, some may be compressed, but amount of elongation and amount of compression magnitude will be same. And second condition, forces applied by all the springs must be in the same direction at the body connected. See here, let us come on the B part. If all the springs are replaced by a single equivalent spring, what should be the force constant of the equivalent spring? See here, again we have redrawn the diagram this way. We have shown the x both the ends spring forces as we had done in the previous part. Now let us replace the all spring by a single spring K equivalent. So extension in the K spring is x. Suppose we had shown here K equivalent, so the x would have been compression. But here the spring force in this direction, and if you have represented equivalent spring here, the spring force will be again in this direction. So what we can write here, K1x, K2x, K3x, and K equivalent x. So what should be K equivalent x? The resultant of all these three forces. So K, the equivalent spring must apply the same force as the combination is applying. Therefore, what we can write? F net is equal to K1 plus K2 plus K3 x is equal to K equivalent into x. Cancel x from both the sides. So what we write here? K equivalent is equal to K1 plus K2 plus K3. So that is the formula. What we are thinking. And such kind of combination we call parallel combination. So in parallel combination, of course, few springs may appear as if they are in series, but condition is what to identify parallel combination. That spring forces of all the springs must be in the same direction, one thing, and second, magnitudes of deformations in each spring must be equal. Parallel combination of springs. Now, what we have learned in the previous example, let us conclude. Springs are said to be connected in parallel if forces applied by each spring in combination are in the same direction. The springs are also oriented in parallel. It means lengths of all the springs must be parallel, and spring force of all the springs must be acting in the same direction to the connected body. Second, in parallel combination or connection, longitudinal deformations in each spring are equal in magnitude. Although some spring may be elongated, some spring may be compressed, but amount of elongation and amount of compression must be equal in all the springs. The combination, if replaced by an equivalent spring, the force constant of the equivalent spring is K equivalent is equal to K1 plus K2 plus K3 and so on. That is what? Simple, very simple relation. And most important point, there is no unique way of combining springs in parallel as there is for series combination, one after other. You have to identify a parallel combination by first two properties. What is that? There is no unique way of combining springs in parallel as there is for series combination. Series combination के लिए एक unique way है, one after other. But parallel combination के लिए there is no unique way. You can see in the previous example. Of course, K1, K2 were appearing parallel and K3 was appearing in series, but again it was in parallel. So for parallel combination there is no unique way, but for series combination there is unique way, one after other. But how you identify a parallel connection? Just by the first two properties. What? Spring forces of all the springs on the connected body must be in the same direction, one thing. And deformations produced in every spring must have same magnitude. So we have concluded about parallel combination. Now let us see how can you use this series and parallel idea. Example 8. All the springs shown in the following system has to be replaced by a single spring. To have the same effect, find the force constant of the equivalent spring. So the what is system is given. There are how many springs? K. This is force constant 2K. It is again 2K. It is what 3K. It is 6K. So there are 5 springs. Of course, by observing this, we cannot say that is which one is parallel, which one is series. But what we can conclude, yes, this 2K and this 2K are certainly in series. and 3K and 6K are certainly in series. So let us first solve this and let us further see what will happen. What? The spring 1 and 2 are in series as well as spring 4 and 5. So replacing them by their equivalent spring constants. So for this in series, what is formula? 1 upon K equivalent is equal to 1 upon K1 plus 1 upon K2. Here we are writing only for two springs. So for this spring 1 and 2, what we get? K1 series 2, 1 and 2 ka series, that is K1 K2 upon K1 plus K2, you can solve it. So 2K into 2K upon 2K plus 2K, it will get K. So that if you replace this series combination by a single spring, what you will get here? A spring of force constant K. Similarly, let us do what we can say for 3K and 6K. So formula is same, 1 upon K equivalent is equal to 1 upon K1 plus upon K2. So K4 in series with 5 is equal to what? 3K into 6K upon 3K plus 6K. Simply it is 2K. So we can replace this spring by a spring of force constant 2K, this by a spring of force constant K, this way. So we have replaced this and this what? By K, and this will remain K, and this combination by 2K, and this spring will keep unchanged. Now this problem is very simple. What? All these three springs are in parallel. So what is force constant? K plus 2K, 4K. All these springs are in parallel. So replacing them by their equivalent spring, what is force constant? K equivalent parallel is K1 plus K2 plus K3. And what is K1? K. What is K2? K. And what is K3? 2K. So K equivalent is K plus K 2K, that is equal to 4K. And it was very simple example. So we have learned so many things for springs. So what my advice is, revise all these ideas thoroughly. Home assignment. Revise all the ideas covered today in this lecture and practice all the examples. Attempt question 20 to 22 in exercise 1 of the module. Means you have to attempt question number 20, 21, 22 because these three questions we have left from equilibrium because earlier assignment was from 1 to 19. So 3 questions here and 2 questions from exercise 3. Attempt question 1 and 2 from exercise 3 of the same module. The module has been posted in the group. So we conclude at this time. Thanks for patient listening. We'll meet again in the next lecture. I am never content until I have conceived a model of what I am studying. If I succeed in making one, I understand. Otherwise, I do not. Sir Lord Kelvin.